Okay, so great. It's an honor to speak in front of this audience. So I'm Steven. Thanks, Ayman, for the nice introduction. So I'm an assistant professor at KAIST. I'm really excited to talk about my recent work on responsible AI techniques for model training and data acquisition. This research was supported by a generous Google AI Focus Research Award. So as a brief introduction of my lab, I joined KAIST 2.5 years ago, and now I have 8 students. My research interests are very aligned with Google, so I like to do big data AI integration, but in addition to that, more recently, responsible AI. So I'm funded by Google, among others, and some other highlights. So I co-coordinate the Google KAIST partnership, and as Ayman said, I previously worked at Google Research for 5 years, and also co-developed Tensorflow Extended, the data infrastructure part. So the photo on the right shows me and my students visiting Google Korea earlier this year. So responsible AI is extremely important, and especially for companies like Google that really deploy AI to the world. And so just to summarize these quotes, it's saying that AI has a significant potential to help solve challenging problems, but it's also critical that it be developed responsibly. So IBM also says that performance is very important, but you also need to build, evaluate, and monitor for trust. So I couldn't agree more. So what are the key issues of responsible AI? So there might be a long list here, but the 2 things that we're most interested in are fairness and robustness. In addition, there's also explainability, value alignment, transparency, and accountability. So we like the first 2 topics because they're very data-oriented and they're very related to each other. So these 2 will be the focus of this talk. So fairness is about not discriminating, and you've probably heard a lot about fairness nowadays. So there's this famous article written by ProPublica, an organization that talks about the Compass software. So this is a tool used by US courts to predict a defendant's risk of committing another crime. So this is called recidivism risk. And the problem is Compass overestimates Black people's recidivism risk compared to white people more than reality. So that's the problematic part. And the reason is that the data that trains Compass is very biased to Black people committing crime. Now, another emerging important topic is robustness against poisoning attacks. And the reason this is emerging is that data is increasingly easier to publish. So there's a tool called Google Dataset Search. So I know I was involved in the internal version. There's also an external version that searches for science data sets. And so it's extremely easy to post your metadata of your data sets. Then Dataset Search just crawls that information and anyone can download that data. And so someone can just post poison data, and then that can be harvested by some web crawler of unsuspecting victims. And now they're using poison data. So poisoning attacks can be very simple, like flipping labels, as you can see in the slide. But recently, they've become increasingly sophisticated and harder to defend against. So we believe that responsible AI needs to be addressed not only in model training, but in all parts of machine learning process. So that means from data collection to data cleaning and validation, model training, model evaluation, model management, and serving. So recently, there are machine learning platforms that support all of these steps, like TensorFlow Extended and MLflow. And I think it's going to be really important to address responsible AI in the entire system. So our contributions are first, the best place to apply a responsible AI is model training, obviously. So we have a recent work called FR Train, Fair and Robust Training. So this was presented recently at ICML about a month ago. We also have a second work called Slice Tuner. So here we look at the model and then we analyze it to determine how much data to acquire per different slices of data so that the model will be fair and accurate. So let's start with FR Train. So model fairness is a very subjective term. I'm aware of at least tens of definitions. And so there are lots of surveys. I personally like the tutorial presented by Suresh in POS 19. So there are largely three classes or categories of fairness measures. One category of measures uses the classifier to measure fairness, like individual fairness, which means similar people have, must be treated similarly. There's also another class that uses the classifier and the protected attribute, where protected attribute is something like gender or race. And so the representative measure here is demographic parity, also known as disparate impact. And I'm going to use this for in this talk. There's a third category that uses the first two and the training labels as well. And so a representative measure is called equalized odds. This was actually proposed by Google. So in this talk, I'm going to illustrate using disparate impact. Also in the paper, we use equalized odds. So what is disparate impact? Well, it's saying that for different sensitive groups, z equals 0 and z equals 1, just think these groups as black and white people, or male and female, the positive prediction ratio must be the same or similar. So I want to quantify that as a real number. So I'm going to use this formula, this expression, where I take the ratio of the two probabilities and take the minimum of them. And so limiting this disparate impact to p% is called p% rule. So now I'd like to show you a motivating example of why we need to take care of both fairness and robustness, and bias and data poisoning. So let's say we have two sensitive groups, black and white. And we have 10 examples where each of these are, say, people. W means white person, B means black person. And the green rectangles here mean positive label. So the first four are negative labels. And let's say we have this real attribute feature called X, and we can sort the 10 examples. And so a very simple setting. So what I want to do is train a classifier that divides, a threshold classifier that divides the examples, such that anything on the right-hand side of the dotted line has a positive prediction, while the rest have a negative prediction. So usually when you're training a classifier, you try to maximize accuracy, which I refer to as a vanilla classifier. And so you can find a perfect classifier here, as expressed by this red dotted line, where all the examples on the right-hand side are predicted to be positive, and they also have positive labels. And the left-hand side examples are all negative, and they also have negative labels. So we've done a perfect job in terms of accuracy. Therefore, accuracy is 1 for this case. What about disparate impact? Well, I'm going to do this computation here. So first, I measure the positive prediction rate of white people. So notice that among the 5 W's here, 2 of them are on the right-hand side of the red dotted line. So that means 2 out of 5 have been predicted to be positive. So the rate is 0.4. For black people, same thing. But here there are 4 black people that are to the right side of the red dotted line. So 4 out of 5 are predicted to be positive. So that's 0.8. So if I take the two ratios and then take the minimum, I get a disparate impact of 0.5. So this is according to this fairness measure, at least, there is some unfairness going on. Okay, so now I'd like to train a fair classifier, which is identical to a vanilla classifier, except that it wants to have perfect disparate impact fairness. So I want to always have DI to be 1. So luckily there exists such a fair classifier here, as expressed as the blue dotted line. So again, I'm going to compute disparate impact as follows. Notice that for both white and black, 4 out of 5 of the examples are on the right-hand side. That means they have positive predictions. So the rates are the same, 0.8, 0.8. So if I take the ratio, it's 1. So that means perfect disparate impact. However, the accuracy goes down a little bit. So out of the 10 examples, we've misclassified the 2 of them, the 2 W's here, because they have positive labels. They have negative labels, but they were predicted to be positive. So we got 8 out of 10 examples correct, right? So that's why accuracy is 0.8. So I went through this TS computation just to make sure this example is understandable. Okay. So now we understand what a fair classifier does, and there are many advanced techniques out there. Now let's introduce data poisoning. So a popular method is to flip labels. In this example, I'd like to flip the labels of these two B's to have negative labels. Okay, so now we've poisoned our data. What do we do? Well, the naive approach is to simply ignore poisoned data. Or why not just perform fair training using our favorite algorithms, and maybe the problem will just go away. But I'm going to show you with this example that it doesn't work that well, and there is a trade-off between accuracy and fairness. So the second approach is to take this two-step approach where you perform some data sanitization where you want to remove the poison first and then perform fair training. So that seems like a pretty reasonable baseline, but I'm going to show you that doesn't work well either through our experimental results. So the final approach is a holistic approach to perform both fair and robust training together, and that's what we're trying to propose. So let's consider the first case. What happens if we ignore poisoning? Well, remember we had this poison data here, and I'm going to train a fair classifier, just like we did before. And it turns out that there exists a perfectly fair classifier here, where disparate impact is 1 and accuracy is 0.8. And this time I'm not going to go through the tedious computation because I think you get the idea. Now, when this fair classifier is actually deployed in production, for example, it's going to be used on clean data. So when we evaluate this fair classifier, we want to do it on the clean data. And so if you do the computation, again, disparate impact remains perfect, but accuracy drops to 0.6. And so you can see that just because we've trained the classifier on poison data, we get a worse trade-off compared to when we train the fair classifier on clean data. So where accuracy drops from 0.8 to 0.6, while disparate impact remains the same. So the bottom line here is that if we ignore poison data, we get a worse trade-off. So we don't want to take this approach. What about the two-step approach? So the problem here is that data sanitization techniques were not really designed to handle data bias that causes unfairness. And same thing for fair training. The fair training algorithms were not really designed to remove data poisoning. So the problem is it's very hard to distinguish poisoning from bias. And so what happens is these individual techniques end up removing, all the problematic data or none of the problematic data. And so I'm going to show you some experimental results demonstrating this observation. So we believe that we should take a holistic approach, and our solution is named FR Train. So I'm going to describe the architecture. So the first part involves fair training. So there is a classifier that predicts recidivism of people. So let's say the output is yes or no. On this side, there is a discriminator for fairness that looks at the predictions and tries to figure out if this person is black or white. So we have this adversarial training. It's just like a generative adversarial network where the classifier doesn't want to leak information to the fairness discriminator. Fairness discriminator wants to figure out, detect that information. So this architecture until now is similar to adversarial debiasing, which is a fair training approach proposed by Google recently. So the novel part of our framework is the bottom part. So in addition to fairness discriminator, we have a robustness discriminator. And this one tries to distinguish whether the data is possibly poisoned or is clean. So in addition to feeding the data from the classifier, we also feed data from a clean validation set, which is known to be clean. It doesn't have to be large and can be constructed with conventional crowdsourcing techniques. And so the discriminator's job is to distinguish poison versus clean. Now the classifier has the additional job of trying to avoid leaking, making the data not poisoned when sending it to the discriminator. In addition, we have a reweighting from the robustness discriminator to the classifier. So once the performance of this discriminator is reasonable, then it's able to distinguish poison data from non-poison data. And that's very useful information. So the classifier can then use those weights to kind of downsample, downsize the, ignore the poison data and only train a classifier on the non-poison data. So this was a high-level explanation of our architecture. We do have some underlying math here. So what I'm showing is exactly the same diagram, but with a little more math. And so we have two theorems that are based on mutual information for interpreting what's going on here. And so the theorem for fairness says that this is the loss term for the fairness discriminator. What it's doing is the loss function value is the same as this mutual information between z, which is the sensitive attribute like race, and y hat, which is the prediction. And so mutual information that's 0 means that the sensitive attribute is independent of the prediction. And this is exactly what disparate impact desires to be. It wants to have the same positive prediction rate regardless of the sensitive group. So there's this interesting connection of what the fairness discriminator is trying to achieve and mutual information. And we add this to the objective function and try to minimize that. And so therefore make mutual information become 0. So we have a similar theorem for robustness. So here we're comparing these two. So V is a random variable that decides whether to feed the poison data to the robustness discriminator or the clean data. And X bar, Z bar, Y bar is what's actually being used by the robustness discriminator. And by making these two indistinguishable or independent, this means that the data from the classifier that's being fed into robustness is indistinguishable from clean data. Okay, so I won't delve into more theory at this point, but that's the high-level idea. So I'd like to show you some evaluation results for FR train. So we evaluated on synthetic data that looks something like on the right-hand side, where we poisoned about 10% of the training data using label flipping. And we used a validation set that amounts to 10% of the training data. And we also have some real data experiments in our paper on the COMPASS and adult census data sets, and the results are similar. So I want to show you this comparison of FR train with the two approaches I mentioned previously. So here we have fair-only algorithms, including adversarial debiasing. And then we have these three methods are the two-step approach, where we perform data sanitization using a state-of-the-art method which we call RML. This is meta-learning based approach, plus the fair-only algorithm. We also make comparisons with approaches that don't care about fairness, logistic regression and data sanitization only. And so the results are as follows. So the clean data column shows the disparate impact and accuracy of training a model on clean data and evaluating on another clean data. For the poison data, we use a method same as what I explained in the motivating example, where we train a classifier model on the poison data, but evaluate it on clean data, test data. And so if you look at the fair-only algorithms, this is a case where we ignore poisoning. You can see a worse trade-off consistent with the example I showed you, where the accuracy goes down. Now, you see something similar for the two-step approach, where accuracy is low as well. And so this demonstrates that it's not a good idea to decouple and run each method one at a time, sequentially. If you look at the non-fairness methods, they don't really optimize on fairness, and so you see low fairness results here. And so FR-train is the only method that obtains high fairness and accuracy. And so the takeaway of this experiment is that it is indeed possible to perform both fair and robust training. So in summary, addressing fairness without or separately from robustness is suboptimal. So FR-train is the first work to holistically perform the two. And this is a very initial work. This is the first work in this area. So I think there are many open problems to be solved. So some of the problems we're thinking about is what happens if we don't have the clean validation set? What if we can't afford to create one? Can we still do fair and robust training? Another problem is what happens if the poisoning is more sophisticated? What if we have a more powerful attack than label flipping? Finally, there's always algorithm stability issues when you're doing adversarial training. And so we like to address this problem better in the future. All right, so moving on to the second topic, I'd like to introduce our work on selective data acquisition for fair and accurate model training. So this work was motivated from my experience at Google when I was co-developing TensorFlow Extended. So I was working on the data infrastructure part, the TFDV. And so there was a component called, TensorFlow model analysis in TFX. It's used to analyze models. So here, the user can slice a data, maybe by country or region or population, and see how the model performs on different slices. And this tool is very useful to identify underperforming slices, the slices that have higher loss than others. So while this is useful for experts, I thought that it was very difficult for non-experts because first you have to have a good understanding of your data. You have to know what feature to use to slice your data. And also there are no action items. So even if you find a underperforming slice, it's not clear how to improve that. So how do you improve underperforming slices? Well, the standard way is to acquire new data so that because usually model doesn't perform well because there's not enough data. And there are many tools available for acquiring new data. So there are dataset discovery tools like Google Dataset Search. There's also crowdsourcing and even simulator-based data generation. Now, this problem is not the same as active learning, which is labeling existing data. This is a problem of finding new data from outside. Okay, so we want to acquire data, but blindly acquiring data, lots of data is not necessarily the right approach. For example, let's say that we have 5 slices here of customers, so America, Europe, APAC, and others. And the size of this rectangle, let's say that's the size of the slice. So we have lots of America data. And so we probably don't need additional America data to train an accurate model. We instead want to acquire data for the other slices that don't have enough data. And the amount of data we acquire per slice may be different. We may want to acquire different amounts of data per slice. So the goal for us is to minimize not only the total model loss, but also the unfairness in losses. So this notion of fairness is a little different from the disparate impact I was talking about. This is saying that for different slices, I want to have the same loss. So this means that if Google is providing some service worldwide, we want to provide the same quality service to all customers. An extremely important measure. So how do we achieve that? Well, a water filling baseline is a good start. So water filling, I mean, we collect same amounts of, make all the slices have the same size in the end. So it's like you're filling in water. But it's not an optimal approach because some slices may need more data to obtain the same model loss as other slices because the data is just different. For example, on the bottom right, maybe we need to acquire more data for APAC customers compared to Europe and Middle East in order to have a better loss and unfairness. All right, so how do we do that? Well, we exploit learning curves of models. So learning curve can be used to estimate model loss on a slice given more labeled data. And so there's a lot of recent work that observes that if you acquire more data, the loss of a model goes down in a power law function. And so here's an image of one of the data sets we experimented on, the UTK face data set. The x-axis is the number of training examples. The y-axis is the loss of a model. And you can see that as the size of the slice increases, the loss decreases and has this power law curve. And I'm showing you two slices, one for white male images and another for black female face images. And you can see that learning curves are quite different. So that's why we may need to collect different amounts of data per slice. And we use the learning curve to optimize and solve an optimization problem to determine amounts of data to acquire. So for now, let's assume that the learning curves are reliable. We can just use them and they have perfect information. But they're not actually perfect, and I'm going to talk about how to cope with unreliable learning curves from the next slide. So here, for now, let's say we're just using the learning curves, and they're informative. So the objective is to find the number of examples to acquire per slice to minimize two things, total model loss, total loss, and unfairness. And so in this formula, there are two things where, those are the two things we're minimizing. The first part is total loss of slices based on our learning curve based estimations. And the second term is penalizing underperforming slices. And so if a slice has a higher loss than average, then we want to give some penalty. So this is what's happening here. And we balance the two terms using a lambda term in the middle. So this is subject to total acquisition cost being within some budget B. And we employ an acquisition cost function that returns a different value for different slices. Because the cost for acquiring the same amounts of data is clearly can be really different depending on the slice. So it may be much easier to collect America data versus say APAC or other region data. So this formulation is actually a convex optimization problem. So you can solve it using any off-the-shelf solver. So some of the audience may be thinking that how do we trust the learning curves? And so indeed, there's an issue of unreliability. So if the slices are too small, then the curves are not really precise because you don't have enough data to fit an accurate curve. And even worse, acquiring data for one slice may actually influence other slices. So this makes the problem really hard. So here in this plot, this is showing how influence happens. The x-axis is number of training examples for a slice called white male. Again, this is the UTK face data. Y-axis is the loss of all the slices. And so as you collect training data for this white male slice, you see a decrease in loss for that slice, the white male slice in blue color. But for most of the other slices, the losses go up, which means there's a negative influence on those slices where the model performs worse on them. But there are some exceptions. So if you look at the white female loss in yellow color, second from bottom, it actually has lower loss. And this is because, interestingly, white female and white male have similar data. And so if you're acquiring data for white male, it's just as if you're acquiring the data for white female. So it actually benefits from the acquisition. So the direction of influence can go both ways, positive and negative. But the important thing is that there is an influence. There is this magnitude of influence. So to explain what's going on in a simple figure, suppose that we have three slices that have different shapes, circles, triangles, and squares. Let's say we have this model that's represented as this decision boundary. So if we acquire data for the triangles only, it's going to introduce some bias. And then that's going to shift the decision boundary to some direction, to the left in this example. And it's going to change the losses of other slices, and therefore their learning curves as well. So that's what's happening when influence occurs. So what's the solution? Well, we like to iteratively update curves. But the next question is, how often should we do this? So there are two competing objectives. So each iteration is very expensive and involves model training on samples and curve fitting. So I haven't talked about the details of how to fit the curve, but it's just an expensive algorithm. On the other hand, we don't want to just keep on using the inaccurate learning curves. And so there must be some sweet spot in between. And so our algorithm can be summarized as follows. First, we ensure some minimum slice size to be able to draw some learning curve. It doesn't have to be accurate. And the slice sizes, I think tens of examples is enough to draw some learning curve. And then we repeat the following. So we first acquire data as long as the estimated influence is not too large. And we then refit the learning curves and then repeat until we run out of budget. So here the key question is, how do we estimate influence? So this is very hard to solve analytically. And so our key approach is to use a proxy, which we call imbalance ratio change. So imbalance ratio sort of captures the bias of the data. It's defined to be the largest size slice divided by the smallest slice size. So the intuition is that if this imbalance ratio changes a lot, then that indicates that there is some influence going on. And so to illustrate, let's go back to our toy example, where if we add red triangles only, then this is adding more bias towards the triangle slice. And if you compute the imbalance ratio, it increases. It used to be 1 here on the left-hand side, but here it's 2. So it increases from 1 to 2. And so that's an indication that some influence, the decision boundary is likely to shift somewhere else. On the other hand, if we increase the slice sizes with the same proportion, so in the bottom example, if we add 1 triangle, 1 circle, and 1 square, the bias doesn't change. And so the decision boundary tends to shift much less. And also the imbalance ratio doesn't change at all in this example. So again, this is a proxy. It's not perfect, but by looking at the change of imbalance ratio, we can infer whether, have a good sense whether influence might occur. So that's kind of the key ingredient in the previous algorithm on deciding how much data to acquire without incurring influence too much. So now I'd like to evaluate slice tuner and compare it with baselines. So I'm going to use these two baselines. One is uniform, where we acquire same amounts of data per slice, and water filling is what I described before. So we use a UTK-based data sets, among others, and we use crowdsourcing via Amazon Mechanical Turk to acquire new face images from the world. And so we create tasks, we pay users, and users actually collect some images from any website. So the acquisition cost per slice is proportional to the average time for a worker to find an image for that slice. And you can imagine this time is different depending on the slice. So here are some numbers. So for white male, it takes an average of 82 seconds to find an image, whereas for the last one, this means Indian female, it takes 104 seconds. So it takes longer. And so we set the cost function to give cost that's proportional to these times. And we consider 3 data scenarios. One is just basic, one is bad for uniform baseline, one is bad for water filling. Details are not too important. The point is we want to consider many different scenarios for extensive evaluation. So the results here show that slice tuner outperforms both baselines. So the left-hand side shows the loss results. The blue plot is when you do nothing. The green and yellow bars are uniform and water filling, respectively. And the red bar is slice tuner. So you can see that slice tuner has better loss than others. Now, on the right-hand side, you can see the unfairness results, where lower is better. And so we use this measure called average equalized error rates, which is basically the unfairness I was talking about. And you can see a much more drastic improvement for slice tuner. So this is where most of the improvement comes from, because we actually explicitly optimize on unfairness. Okay, but what if the learning curves are unreliable? So we also have experiments on
tiny slices, where slices have tens of examples. So here, I just want to illustrate how hard it is to fit the curves. So on the top right, you can see very jagged lines of losses, and we're trying to fit a very clean curve using this noisy data. And so by themselves, the learning curves are not really reliable. But if you look at the results, a slice tuner still outperforms the two baselines. And the reason is that slice tuner can exploit the relative differences of learning curves in terms of the loss and steepness. So even if individually the learning curve is not reliable, it's the difference that matters. And so as long as that information is available, slice tuner exploits that difference. And so in the worst case, where learning curves are totally random, a slice tuner just falls back to the performance of one of the baselines, which is not a really bad option either. So to conclude the entire talk, responsible AI needs to be addressed in all parts of the machine learning process. And I think we just scratched the surface by proposing two systems, FR-train and slice tuner. And we believe that there are plenty of open problems to solve. And I really look forward to continuing collaboration with Google for solving the problems. So thanks for listening, and I'm happy to answer questions.